Good afternoon. Today, our group would like to take some time to demonstrate our senior design project, Project Lightbeam.
So what is Project Lightbeam? Project Lightbeam is a small-scale roller coaster that uses LEDs to simulate real-life roller coaster vehicles. This project will allow students and others to learn how controls logic works. One of the team's goals is to develop a model that adheres to relevant industry requirements and is both economical and reliable along with keeping safety in mind.
Here are the engineering requirements for our project. Highlighted in yellow are the requirements that the team has decided to demonstrate. The ability to demonstrate safety block zones, safe stopping distances, and safe dispatch times are the primary focus of our project. These specific engineering requirements were chosen due to the experiences from the themed entertainment industry. After thorough testing, our project was able to meet the engineering requirements with these results.
Here we have an outline of the proposed design for our project. On the left, we have the operator console, and on the right, the roller coaster track layout.
Here's an example of a roller coaster that exists today. On the left is an example of a real operator console that features similar features to our operator console. On the right is an image of two zones, the unload station and the load station. Notice how the blue vehicle is lined up behind the green vehicle. The blue vehicle is in the unload station, which is a zone right before the next zone, the load station. The control system will know that there's currently a vehicle occupying the next zone. Therefore, it will then command the blue vehicle to not enter the load station. This block zone logic will be demonstrated later in the presentation.
At the start of operations, all our sensors need to be recalibrated to adjust to the lighting in the room. Once all the sensors are calibrated, we then turn on the coaster and dispatch the vehicles. As the vehicles go through the track, you can see that the vehicles will not proceed to the next zone because of the safety block zones. Notice how the red vehicle does not proceed to the next zone until the blue vehicle has cleared that zone. For example, let's say something malfunctioned and would require us to stop all the movement from the coaster. Our operator then hits the e-stop and all vehicles stop their movement. After we reset the e-stop, we then reset the console and we were able to dispatch the vehicles again. Now let's say that we need to stop movement in the station because someone jumped into the track. We then hit the station stop to prevent all motion from entering or exiting the station. Notice how the green vehicle stops in the zone prior to the station and does not enter it. Once we reset the station stop and reset the console, we can dispatch the green vehicle and allow it to enter the station. Additionally, when we turn off the console in the middle of operations, the vehicles also stop in their place. Our coaster is able to run continuously throughout the day and provides a unique experience for those who want to learn about control systems and roller coasters.
Here is an outline of our hardware. We will be using an Arduino as the MCU, which will communicate to two multiplexers. And here is a video showcasing the model. Here we have the operator console. This operator console has the ability to start and stop the coaster and manage the overall safety protocols of the roller coaster. The operator console sends the button signals to the Arduino. Here on our PCB, we have our power module, the two multiplexers, the Arduino, and all our peripherals connected in one central area. The Arduino is the main component of our project as it controls the LED strip to accurately represent the vehicle locations. Additionally, the Arduino is the component that handles the decision-making of the coaster. Next on the PCB are the two multiplexers. One of the multiplexers is in charge of the photoresistor sensors, and the other handles the operator console and the individual LED indicators. And finally, our power module. This power module takes in 120-volt AC and converts it to 5 volts that can be consumed by the entire board. From the PCB, we then have our multiplexer that controls photoresistor sensors and LED indicators that are located throughout the track. In order to detect the vehicles, the photoresistors are positioned in a way to receive light from the LED strip. The vehicles themselves are represented with 4 LEDs lit up at the same time. To differentiate between the vehicles, each vehicle's beginning and end LED is set to white, while the 2 middle LEDs are set to different colors. We have the ability to put as many vehicles as we want and can change the colors and/or length of each one. However, to maintain our block zone logic, we can only allow n-1 vehicles, with n being the number of zones in our coaster.
These signals from the operator console are then passed on to our oh my god. These signals from the operator consoles are then passed on to guys, I'm tired, I'm sorry. Okay. last one. These signals from the operator console are then passed on to other functions within the code to manipulate the LEDs to react accordingly. For example, for the emergency stop function, we monitor to see if the emergency stop state has been cleared. If the e-stop was not cleared and we attempt to dispatch a vehicle, the system should know that there is currently an e-stop and it must be cleared before sending any vehicles. Additionally, the dispatch function should not occur unless an enable has been granted. All of these redundancies are necessary to ensure that the system will behave appropriately and safely.
These are our engineering requirements that we will be demoing. Our first requirement is the ability to stop the vehicles in a safe distance. The second engineering requirement is the ability to initiate motion in a safe state and speed. And last but not least, we require our coaster to demonstrate the block zone safety logic to ensure a safe and consistent ride for the guests. Now let's move on to the demo. Each roller coaster has a safe stopping distance, which is the minimum distance required for a roller coaster to come to a complete halt under controlled conditions. For our test, we measure the safe stopping distance by triggering the e-stop and measuring how many LEDs the vehicle stops at after pressing the e-stop. Our goal is to have the vehicle stop in less than 2 LEDs, which is about an inch. If this were to scale, our coaster should be able to stop in less than a foot. This stopping distance ensures that vehicles are able to stop in a timely manner to avoid collisions. After 10 trials of performing the same test, our vehicles stop at about 1.3 LEDs after pressing the e-stop, which is within our engineering requirements. Roller coaster designers and engineers meticulously calculate and test braking systems to ensure that they can effectively slow down and stop the coaster within a predetermined distance. Emergency braking systems are also incorporated to handle unexpected situations. The safe stopping distance is a critical parameter in ride design, and it is established through rigorous simulations, modeling, and real-world testing. Regulatory authorities and industry standards often set specific requirements for safe stopping distances, and theme parks must adhere to these guidelines to obtain operating permits.
The next engineering requirement that we would like to demonstrate is the safe dispatch speed. A safe dispatch speed for roller coasters refers to the maximum speed at which a roller coaster train is allowed to begin its journey with passengers on board. To measure this, we start our timer the moment the dispatch button has been pressed and stop the timer when the vehicle takes off. As a user, it is crucial for there to be no lag between the console and the LED strip. Our goal is to have the vehicles dispatch within a second. After 10 trials of our test, our vehicles dispatch at about 0.51 seconds each time, which is within our engineering requirements. The safe dispatch speed ensures that the coaster can navigate through its twists, turns, and drops while maintaining a balance between excitement and safety. It is crucial for preventing excessive forces on the riders, minimizing wear and tear on the ride components, and ensuring that the coaster can safely navigate all elements of the track. Theme parks and amusement ride operators follow industry standards and regulatory guidelines to establish and enforce safe dispatch speeds. Regular inspections, maintenance, and performance testing are conducted to verify that the roller coaster continues to meet these safety standards over time.
For the block zones, which is a part of the overall functionality, all vehicles should only enter the next zone if the next zone is cleared. To demonstrate the block zones, we execute another station stop to show that the vehicle behind it will not enter that zone because it is deemed occupied. The occupied state is determined by the sensors placed at the beginning and end of each zone. Once the next zone is cleared, then the vehicle is allowed to proceed. As the vehicles traverse the track, notice how there is at least one block zone between each vehicle. In today's coasters, due to the multiple vehicles, having this zone spacing ensures that vehicle-to-vehicle collisions do not occur. Block zones play a crucial role in ensuring the safety and efficient operation of a roller coaster. These designated sections of the track serve as a safety buffer. By dividing the track into block zones, roller coaster designers can control the speed and position of individual coaster cars. This allows for a controlled and synchronized operation, ensuring that no two cars can enter the same block zone simultaneously. In the event of an issue or emergency, block zones facilitate a swift and automatic stoppage. Block zones are integral to the coaster's control system, acting as a fail-safe mechanism that keeps the coaster's operation in compliance with the rigorous safety standards and prevents potentially dangerous scenarios. In this slide, we outline the block diagrams used to drive our project. We hope you enjoyed our demonstration of Project Lightbeam. Thank you for your time.